All right, let's finish up 1.4. So the rest of this section also has to do with precise definitions of limits. So we're going to look at limits as x approaches infinity or negative infinity. And then we're also going to look at limits as x approaches a finite value, but there is no finite limit, right? So the limit is infinity or negative infinity. So we'll look at those as well. But here's the precise definition, okay? So let's say that f of x is a function that's defined for all x in some infinite open interval, okay? If we say that limit as x approaches infinity of f of x equals L, then that means that for all epsilon bigger than 0, there exists some number n, some positive number n, such that if x is bigger than n, f of x is going to be within epsilon units of L. So given any epsilon, you're going to be within, after a certain cutoff point, you're going to be within epsilon units of L if the function does indeed approach L as x goes to infinity. And then the limit as x approaches negative infinity is similarly defined, right? It means that for all epsilon bigger than 0, there's some cutoff value n, a negative value for n, such that if x is smaller than n, f of x is going to be within epsilon units of L. So here are pictures of the two definitions, right? So the first definition is saying that if the limit as x approaches infinity of this function equals L, then what that would mean is that there would be a cutoff point, which we're calling n, such that for every value of x bigger than that, you're going to be within epsilon units of L, right? So you're going to be within the epsilon neighborhood, okay? And this is true regardless of how big or small epsilon is. So in particular, if epsilon is really, really tiny, if the limit as x approaches infinity is in fact L, then no matter how small epsilon is, eventually you will have a cutoff point where the function value is within that epsilon neighborhood. Okay? And then the second definition is similar, it's just it's going in the opposite direction, right? So if you have this kind of situation, and again, the limiting value is L here, okay? If that's the case, then there's going to be some cutoff point, which we're calling n, such that any x less than that value is going to have its output within the epsilon band, right? Within the epsilon neighborhood. Okay. So let's practice doing some proofs with that idea. So this is the third example, by the way, that I'm giving you from section 1.4. That's why I'm labeling it 3. But let's prove each statement. I'm just going to give you 2 examples. I'll give you one of each kind of limit. So let's prove that the limit as x approaches positive infinity of x plus 1 over x minus 1 equals 1. So we're going to start off just like we usually do with epsilon delta proofs. We're going to say let epsilon be greater than 0. This time we don't have a delta, right? This time we have an n. We're looking for a cutoff point, n. So we're going to say let n equals something. And we're not sure what yet, so we'll just leave it blank. And now suppose or assume, right, that x is greater than n. Then we need to show that absolute value of f of x minus L is less than epsilon, right? So we need to show that absolute value of x plus 1 over x minus 1 minus 1 is less than epsilon. Well, let's simplify this a little bit. If I think of this as 1 over 1, and then I get a common denominator of x minus 1, I'm going to have and then x minus x is 0, 1 minus negative 1 is 2. And I suppose I could really drop the absolute value bars because x is a positive number, and it's sort of implied that x is a really big positive number, so that x minus 1 is going to be positive, and 2 is of course positive, so this is just 2 over x minus 1. Now, if x is bigger than n, then 2 over x minus 1 is less, or sorry, oh, let me think about that. Yeah, no, that's right. I'm sorry. Yeah, that's right. If x is greater than n, then 2 over x minus 1 is less than 2 over n minus 1, right? In other words, n is the bigger number. So if you replace x with n, this overall fraction is going to get smaller because a bigger denominator means a smaller fraction, right? So, so this is less than 2 over n minus 1. Okay, and we know that because we're assuming that x is larger than n. So now, we need for this to equal epsilon, right? So I'm going to do a little scratch trick. I'm going to say 2 over n minus 1 needs to equal epsilon. So that means 2 needs to equal epsilon times n minus 1. And I'm trying to solve for n, so I'm going to say 2 equals epsilon n minus epsilon. I'm going to add epsilon over to the other side, and then divide by epsilon. So it looks like n has to equal 2 plus epsilon divided by epsilon. Right? So if n is 2 plus epsilon divided by epsilon, then we get this is equal to 2 over 2 plus epsilon over epsilon minus 1. I'm going to multiply by epsilon in the numerator and denominator to clear that compound fraction. Then the epsilons down there cancel. I get 2 epsilon over 2, which is of course just epsilon. And there we go, right? So that concludes that proof. So given any epsilon you like, just let n be 2 plus epsilon divided by epsilon. And there you go. That will do the trick. Okay. So let's do another one. Let's do limit as x approaches negative infinity of 1 over x equals 0. All right, let's see. So let epsilon be greater than 0. Let n equal something. Don't know what yet. And then let's suppose, now for limit as x approaches negative infinity, remember that n is a negative number here, and we want x to be even smaller than that, right? We want x to be even further away from 0. So suppose that x is less than n. Okay? All right. So we want to show that absolute value of f of x minus L is less than epsilon. So we want to show that absolute value of 1 over x minus 0 is less than epsilon. Well, this is just absolute value of 1 over x. Okay. All right, so very good. So this is So one thing that I'll point out here is that, remember, n is a negative number. So what we actually have is this statement, right? If this is the case, then when you look at the absolute values, absolute value of x would have to be greater than the absolute value of n, right? And if absolute value of x is greater than absolute value of n, then absolute value of 1 over x would be less than absolute value of 1 over n. Whoops, absolute value bar. Or another way to say that, I guess you could say this is 1 over absolute value of n. Now we need for this to be, we need this to equal epsilon. So, so I think what I'm going to do is let n equal, remember n has to be a negative number and epsilon is a positive number, so this is a little tricky, but I'm going to let n be negative 1 over epsilon. That way, you know, epsilon is positive, that means n will be negative just like I need. And when I plug this in here, I get 1 over absolute value of negative 1 over epsilon. That's 1 over epsilon, which is just epsilon, okay? Which is what I needed to happen, right? So that concludes that proof. Okay. Let me give you another example. Maybe not a proof so much as just you'll see a problem kind of like this on the homework. So let's find the smallest value of n, positive n, such that for each x in the interval n to infinity, f of x equals 1 over x cubed is within epsilon units of the limit L equals 0. Okay. In other words, let's find the cutoff value. Let's find the cutoff value n, so that f of x is going to be within epsilon units of 0 for epsilon equals 0.1. Actually, I did get this example straight out of the textbook, and they ask for these 3 values. But what I'm going to show you is that it's really the same question over and over again. Oops, this should be epsilon equals 0.001. It's really the same question over and over and over again. So let's work out the solution. Okay, so in all 3 cases, what we need is for absolute value of 1 over x cubed minus the limit 0. We need for this to be less than epsilon. Now, we know that if x is in the interval n to infinity, then x is greater than n, okay? And if x is greater than n, right, this is 1 over x cubed. If x is greater than n, then x cubed is greater than n cubed, which means 1 over x cubed is less than 1 over n cubed. So this is less than 1 over n cubed. And I'm dropping the absolute values because I know n is a positive number, right? N is a positive number. And I need this to equal epsilon, right? So this is the equation that I need to solve in all 3 cases. I need to solve 1 over n cubed equals epsilon. So for part A, let's say 1 over n cubed has to equal epsilon, 0.1. So that would mean n cubed equals 1 over 0.1. In other words, n cubed equals 10. In other words, n would equal the cube root of 10. Okay, That's the smallest value of n, such that f of x is going to be within 0.1 units of 0. Okay, so that's the smallest one that'll do it. For part b, then it's going to be similar. We're going to say 1 over n cubed equals 0.01. So in other words, n cubed would be 1 over 0.01. In other words, n cubed would be 100. So that n would be the cube root of 100. And you probably see where this is going for part C, right? So I'm not going to show all the details. But for part C, you should get n equals the cube root of 1,000, which is 10. That one actually comes out pretty nice. Okay, but that's that, right? So that's how you do that kind of problem. I'm not going to show you how to do every single kind of problem on the homework, but you know, sometimes when all we do in class is proof, and then suddenly you're asked a question like this, you're like, what in the world are they asking for? So I just wanted to give you an example of something like that. Okay, so those are infinite limits. So next thing I want to talk about is finite limits. So I want to go back to the finite limit idea. But look at what happens when x is approaching a finite value, but f of x is approaching infinity or negative infinity. And let's give precise definitions for those things, and then we'll be good, right? Then we'll be done giving our formal definitions of limits. Okay, so here we go. So let's say f of x is defined for all x in some open interval containing a, except possibly at a itself. Okay, so maybe it's not defined right at a, but it's defined on some open interval containing a otherwise. Limit as x approaches a of f of x equals infinity means that for all m greater than 0, there exists a delta greater than 0 such that x minus absolute value of x minus a less than delta means that f of x is greater than m. So here's a picture of that, right? We're saying that if you choose some cutoff value m, you should be able to find a delta, so that if you are within delta units from a, f of x is going to be bigger than m, right? F of x is going to be bigger than m, so it's going to be up here, as you can see in this diagram, right? It's like if you're within this interval. So like in particular, if you were this value right here, right? If you were this value right here, then obviously f of x would be bigger than m, right? It would be bigger than m. So that's what this definition is saying. And definition 2 is similar, right? Limit as x approaches a of x equals negative infinity means that for all m less than 0, so for all negative cutoff points m, there exists a delta greater than 0 such that if x is within delta units of a, f of x is going to be smaller than m. And here's the corresponding picture for that, right? So if you have some cutoff value m, we should be able to find delta neighborhood, right? Such that if you're inside of that neighborhood, the output, if the input value is inside of that neighborhood, then the output value is going to be smaller than m. It's going to be less than m. Okay. So that's the idea behind those two definitions. And let's give some examples. We're almost done. I'm exhausted. I recorded part 1 just a second ago, so I've been lecturing now for like an hour and a half. I need to pause this. I've got to train. Okay, so let's prove the following. So let's prove that the limit as x approaches 0 of 1 over x squared equals positive infinity, which, by the way, should make sense, right? This is what the graph of 1 over x squared looks like. So as you get closer to 0, f of x goes off to infinity, right? Okay, so let's prove it. So we're going to start off by saying, okay, so let n be bigger than 0. Let delta equal something, we're not sure what yet. And then suppose, or assume, that absolute value of x minus 0 is less than delta. Okay, so what that really means is that absolute value of x is less than delta. Okay, so we need to show that this is a little different. Right, because we're not going to try to show now that absolute value of f of x minus L is less than epsilon. What we actually want to show is that f of x is greater than m. We want to show that f of x is greater than m. So let's see if we can do it. So we want to show that f of x, 1 over x squared, is greater than m. Okay, well, we know that absolute value of x is less than delta. So if we wanted to be really specific, I guess we could say this, right? We could say well, this is equal to, 1 over x times 1 over x. And if you wanted to, you could even put absolute values around the x. If absolute value of x is less than delta, then 1 over absolute value of x is greater than delta. Or greater than 1 over delta, rather. Right? So that's like a standard trick about inequalities. It's like, 2 is less than 3, but 1/2 is greater than 1/3. Right? So if you flip both quantities over, you can do that as long as you change the direction of the inequality. So if 1 over absolute value of x is greater than 1 over delta, then what we have here really is that this is greater than 1 over delta times 1 over delta, which is 1 over delta squared. We just need to show that this is, right, we have our greater than sign, which is what we need. So we just need to show that this is equal to n. So basically we just need to solve this for n, right? So we would say, okay, so a little bit of scratch work down here. So a little bit of scratch work, we would say we need 1 over delta squared to equal n. That means we need delta squared to equal 1 over m. That means we need delta to be 1 over square root of m. Right? And so if that's the case, then we get this is 1 over square root of m squared, which is 1 over m, which is just m. So f of x is greater than m. Right? So there we go. That's that one. Let me give you one more, and then I can take a break. And you can too. A well-deserved, well-earned break. So one more. Let's do limit as x approaches 3 of negative 1 over x minus 3 squared. This thing goes to negative infinity. Which makes sense, right? It's like if this is 1 over x squared, then this has just been shifted right 3 units so that your vertical asymptote is at 3, okay? But it's also been flipped over. So instead of shooting off to positive infinity at 3, you're going to be shooting down to negative infinity at 3. Let's prove it. Now these things, I'll be honest, like these kind of throw me through a loop a little bit. It's always easier for me to think about this in terms of absolute values and stuff. So let me show you what I mean. So we're going to start off by letting m be less than 0. And right off the bat, that's just strange for me because I'm so used to having epsilon be bigger than 0 or n bigger than 0. This is the only case where we let the number be smaller than 0. But here's how I help it make sense in my mind. If this is the case, right? So if m is less than 0, then absolute value of m would be greater than 0, of course, right? So just bear with me. It's a little bit easier for me if I think about it in these terms. So then let delta equal 1 over the square root. Ooh! Now, we need to discover this first. I'm sorry. I was getting ahead of myself. We'll come back to what delta is. Let delta be something. We don't know yet. And then let's suppose that absolute value of x minus 3 is less than delta, whatever delta is. Okay? Now, we need to show that f of x is less than m. But what I'm actually going to do is I'm going to show that absolute value of f of x is greater than absolute value of m. And if I can succeed at doing that, then that will imply that f of x is less than m. Because notice that f of x is going to be negative for any value, and m is also a negative number. So if absolute value of this thing is bigger than absolute value of this thing, well then, without the absolute values, this must be smaller than that. Okay? So absolute value of f of x equals 1 over x minus 3 squared. And I know that the absolute value of x minus 3 is less than delta. So by a similar line of reasoning to what I did up here, just replace the absolute value of x with absolute value of x minus 3, right? And what you're going to get is that this is greater than 1 over delta squared. And that's why I was saying up here that delta needed to be 1 over the square root of something. In this case, delta needs to be 1 over the square root of the absolute value of m. Okay, because if I replace delta now with this quantity, I'm going to get 1 over square root of absolute value of m. That's going to be 1 over absolute value of m, which is just the absolute value of m. So I've shown that absolute value of f of x is greater than absolute value of m. Since f of x and m are both negative numbers, that must mean that negative 1 over x minus 3 squared is less than m. Okay, and that does it for that one. So there you go, a bunch of limit examples. Hopefully you're well equipped now to tackle the homework. So I will see you in the next section.